B. Then on top of that now you have, very similarly to the unsupervised case, the dot product between the students and the teacher. All the replicas of the student and teacher. I don't want to do the calculation, it's always the same stuff, right? So it has been done in many papers, so you can find them. If you want references, please ask me. And essentially the picture you get is this one. So look at the top panel here. The generalization error, so that's the probability that the student makes a mistake, starts when you have no data to 1/2 because the student is completely random, right? So it's essentially orthogonal to the teacher. And then as you have more and more samples, so alpha increases, what you see is that this generalization error is decreasing as essentially at large alpha, some constant which is known over alpha. And the training error is always equal to 0 because this is a realizable rule, right? I mean, there exists a student which can actually do exactly what the teacher does. Okay? So you see that the decay of this generalization error, so that's nice. This is true for continuous perceptron with continuous weights. If you have discontinuous weights, let's say for instance the JIs are plus or minus 1, then you can have discontinuous learning curves. So I'll come to that in the multi-layer architecture actually, where you see something similar. Now there is the interesting case of what happens if you have a teacher which is more powerful than the student. That may happen. Okay, so let's say we have a student which is a perceptron and the teacher can be a more complex machine than this one. Yet, so the question is what the student is able to learn. So the student will have some learning curve which is of this type. Starting from 1/2, it will decay to some asymptotic level, which in principle will not be equal to 0, simply because it cannot compute the same thing as the teacher. And if you look at the training error, it will be 0 up to the capacity we have computed yesterday. And then it will increase and reach the asymptotic level of the generalization. So this is the standard scenario you would get, right? Is it okay? There is nothing really surprising about that. Okay, so what I would like to do today now is to move to two more interesting aspects. One is more interesting architecture than the perceptron, so a multi-layer neural network. So I won't go to deep networks. I will do just a 2-layer neural network, which is the simplest, more complex architecture above the perceptron, right? Beyond the perceptron. And still, I mean, there have been a lot of works in the 90s on this architecture, and you see that the picture is actually not so simple, and it's quite interesting because it tells you how, it shows you how the learning scenario is different from the perceptron one. And there is a big qualitative difference, which I think is interesting. And then, if I have time, I'd like also to talk to learning in a recurrent neural network, which is similar to the perceptron. I will explain how. But with more interesting data. Here, the inputs are totally random. Okay? There is no structure in the inputs. But in many applications, actually, data are structured. And you already heard about that in many lectures. So the question is, what happens if you want to do, you want to embed structured data in our recurrent neural networks? And I will specifically look at the case of embedding many low-dimensional manifolds in a high-dimensional network, right? And I will give you some motivation to do that. You have strong motivation to do that coming from machine learning. So for instance, in his first lecture, Mark told you about the finite dimension of MNIST, right? So you could imagine what happens if instead of having 10 digits, I have an extensive number in digits. I have many, many digits, right? And they are all finite dimensional. But then suppose I have L digits and in base L, so for instance. And then I would like to know how many classes like that, digits, a manifold, I could embed in a recurrent neural network with n neurons. So what is the trade-off between n and L? Okay. And then there is a strong motivation coming from neuroscience, and I know that some of you are very much interested in neuroscience, so I would like to talk a little bit about that. Okay, so in the first part, I'll talk about multi-layer neural networks, and this is really the simplest multi-layer neural networks you can think of. So the architecture is very simple. I have one layer of inputs, as in the perceptron, one output. So the inputs will be the xi, the output will be y, and then I have a hidden layer here of units which I will call the tau L. So all my units can be equal to plus or minus 1. Okay? So they are all binary units. And I have n input units, k hidden units, and 1 output. Okay? So now how do I connect all these units together? Then I will have connection from the hidden units to the output. And then I will have also connection from the hidden units to the inputs. And I will assume in a first step, then I will go back to that at the end, because it doesn't change so much, that I have a tree-like architecture here. So that means that each hidden unit is looking at a subset, essentially, of n over k inputs. And there is no overlap between the different hidden units, right? So it's the main effect of that is that, okay, so the hidden units are looking at, let's say, some subspaces of the input space, right? And the main effect of that is that the number of degrees of freedom you want to learn here, these parameters, these weights here, right? So for each hidden unit, you have n over k weights instead of n, right? So of course, this machine is less powerful than the machine where you can have everything. But you have also much less degrees of freedom rates to learn from the data. So it can be useful in some cases, right, to have faster learning. But you will see actually when you forget about this tree-like architecture, it doesn't change much the results. I will come back to that at the end. So this is my first simplification. And my second simplification is that actually I will not try to learn the weights here. Okay? So what I mean is that I will assume that y is a function of tau 1, tau 2 up to tau k. And this function is known. It's called, if you want, it used to be called a decoder. So essentially, you are not trying to adjust the function to better fit the data. That would be nice. That would be interesting. This is what you should do. But I will not do that here. So it's a limited machine, right? So there was some kind of examples of decoders that were studied a lot in literature. So I will cite two of them. The parity decoder, which is simply the f is equal to the product of L from 1 to k of tau L. So it's something which is plus or minus 1. It's a product of plus minuses. And the committee decoder, or majority decoder, it's the same thing, which is simply looking at the most frequent sign among the TL. So that's the sign of the sum over LTL. Tau L, sorry. Which is again a plus or minus 1. And you will see how these different decoders may actually affect a lot the properties, the learning properties of this machine. Okay?
All of the new ones are plus minus 1?
Yes, everything is plus minus 1. Okay, yeah. Okay, so I won't do the full calculation, but I think I would like to really stress what is new and interesting here compared to the perceptron, because that's the important point. So now you have, after 3 lectures, you have become experts in replicas, so you know how to do these things, you know, at least within the replica symmetric assumption, because that's something we have done several times. So let me write just the initial expression for the volume, but I won't do more calculation than that. And then what you would get if you did completely the calculation as people did in the 90s. So the volume, so let me call J1 here the weight vector for hidden unit 1, and JL the one associated to hidden unit L. And there are k of them, right? So the volume associated to, suppose you have some x mu's, which are the inputs here, and the corresponding y mu's, which are the output. So this volume will be the integral over the k weight vectors, which I will assume to be normalized. So it's very similar to what we have done yesterday, except that instead of having a single perceptron, we have actually k perceptron. And now we are going to combine them in order to compute the output. Okay, so this is that. And then now I will sum over all the possible values of what I call here, and that's a very important thing, these taus here. So this hidden layer, I will call, it's a representation layer. Yes?
Why do we iterate over L? Is J not over I?
Sorry, can you say it again?
J, this weights, why do we iterate over L?
So JL for me, okay. So it's a vector which is of dimension n over k.
Ah, okay.
Okay, so you have n. So this is in dimension n over k. Okay, so very high dimension. Okay, so here I will sum over all possible representation, and what is a representation here? It's a vector of k pluses or minuses, and that I have to specify for each input mu. So it's a tau L mu here, which is plus or minus 1. I'll come back to that. Let me finish the expression. And then, okay, so first of all, I want to be sure that I'm mapping my x onto this representation here. So I have a product of all inputs and all hidden units of theta tau L mu JL dot x mu. Okay, and then I want to be sure that once this representation I have here is actually correct, so that it's mapped onto the output, right, the desired output. So this is multiplied by a theta, a product of a mu, theta y mu, f of tau. Sorry, sometimes I have a mu which is below, sometimes a mu which is above. That's really bad. Sorry about the confusion in the notation. Let's put everything below. Okay, so this is tau 1 mu up to tau k mu. Do you agree on this expression? Right? So what I'm saying is that I don't care about the representation. The only thing, so I will sum over all of them, right? And I just want to select the representation which are compatible with my output, and that should be true for all the patterns, all the inputs mu, right? And for each possible, which good representation, I will see what is the volume of a JL that corresponds to that.
So that's just imposing that tau is the sign.
Exactly. Right. Yeah. So I'm doing this. Maybe you find it a little bit involved, but you will see very soon why I am doing that. Is it okay?
In fact, Dirac it should be n over k, right? Because they're just n over k units.
Here?
The next one, Dirac JL squared minus n over k.
Here?
Yeah, inside the Dirac.
Oh, yes, sorry. Excuse me, you're right. Absolutely. Okay? So, now, okay, so you can do replicas with that. So what do you do? Well, you do the usual stuff, right, with replicas. So you will take the nth power, small nth power of this, then you will average over the quench variable, which are the x mu's and the y mu's. So let me assume in the first step that I have just purely random outputs, right? So I don't want to, it's a capacity problem, it's a null model problem. I'm not trying to generalize anything, it's just pure noise. So if I do replicas, I have something like that. And I think you will trust me that this is going to be something like exponential of n, the size of the number of inputs, and the number of replicas when n is small. And then there will be some function, and I put here a subscript rs within the replica symmetric assumption of q, and that depends on alpha. That depends also on k, obviously. So here I've made the assumption that the matrix QAB, that's the kind of order parameter I get when I do the calculation. This thing here, I make a double assumption. First, it does not depend on L, which is reasonable, right? Because you have clearly a permutation symmetry between the different hidden units. And it does not depend on the pair of indices A and B, which is the replica symmetric assumption. Yes?
And it's just QL and not QL of K because we have not fully connected.
It's
We had fully connected instead of the...
Yes, you would have overlap between different vectors associated to different units. So that makes my life simpler, right? Okay, so I'm assuming, so that defines a single Q, and this is it, right? Okay, and now, as we did yesterday for perceptron, you look at what value of Q is minimizing this quantity, and this value here, if I plot it as a function of alpha, then it starts from 0, and then it will grow, and then it will hit 1 at some value alpha c, which is a function of the decoder f, right? Depending on the machine I'm looking at, I will get a different alpha c. So the calculations are a little bit involved, so let me just give you the results it gives. So for alpha c for the parity machine, which I call par, it gives something which when k, so it depends on k, when k is large scale as k squared, and alpha c for the committee machine, which I call com, gives something which is square root of k. There are some multiplicative constant I don't care about. So the problem with this prediction is that they are completely wrong. And you can see that in many different ways. First, they are not self-consistent. If you do the local stability analysis, so you have to be careful here, compute the Hessian and compute the eigenvalues and so on, you see that there are some instabilities, right? So actually, well before reaching this capacity, there are instabilities somewhere here, right? So this is completely wrong. This is seen also numerically. If you try to actually really learn some input-output association with such a machine, and people have done that using, for instance, simulated annealing with some cost function, right? And you have different learning algorithms you can think of. You see that the capacities that you get numerically are much lower than those ones. So what I would like now to see is why is the replica symmetric ansatz here completely, why does it fail? Okay, and that's an interesting question.
Sorry.
Yes?
So we are keeping k fixed and not scaling with n?
Yes, you are right. So sorry, I was not clear on that. So I'm interested in the large n limit first, and then large k limit. Having n and k of the same size and with the same scaling, that is a complicated problem, which is somewhat related to the open problem I suggested. So it's not easy. But okay, let's.
And also to the one that Mark suggested, the dictionary learning.
Yes. Okay, you're right. So it's complicated. So, but really here, everything I'm trying to get the very simplest thing above the perceptron, right? Okay, so in order to get some insight of that, I will do something. I will just, take this sum here, and I will put it in front of the integral. You agree that it doesn't change anything about the volume, right? Okay, so let me do that. So this I put here. And then you see that the integral over J here now depends on this tau L mu, right? So everything which is left, so this thing here and this thing here, I call this the volume associated to the representation tau, which depends on the data. Okay? And if I sum over all possible representation, then I will get my interesting volume here, the full thing I would like to compute. So it's interesting to spend a little bit of time to understand what that means. So what is tau here? So this big tau for me is actually the set of tau L mu's. Or if you prefer, you can think about it as a matrix. It's a matrix here, which has p different rows. So each row is a mu, right? All the x mu, y mu, and it has k different columns. Okay? So each column is a hidden unit, and each row is an input, right? And it's full of pluses and minuses everywhere. Do whatever you want and so on, right? So some of the taus, many of the taus actually, are not good, right? So in the sense that if you look at this condition won't be satisfied, so the v tau is simply 0, right? So you don't care about that. You are interested in the one which correspond to the good mapping, right? I mean, the one that are equal to 0, they don't contribute to the sum, so we don't care about them. So my question is the following. First of all, how many representations do I have? So the total number is easy to compute. The total number is going to be C of k to the p. It's certainly exponential in the number of input-output pairs. And C of k is the number of vectors of tau 1, tau k, which are actually compatible with one possible output. So for the parity machine, you see, suppose y is +1. Then you have k bits, which can be plus or minus 1. And you ask how many of them are such that the product is equal to +1. And you see that it's just half of all possibilities. If you have -1, it's the same thing, obviously. So for the parity machine, C of k is simply 2 to the k minus 1. That's the maximal number of representation you can think for one vector, right? You agree? For the committee machine, then what you have to do is to look at all the possible vectors of +1 or -1 so that the sum of the signs is, for instance, positive or negative. So for instance, suppose you want to realize a plus, so you have to choose at least half of the taus which are plus, right? And then you are done. So this is, so you can see it as a sum of binomial coefficients, so it's a sum for m running from the integer part of k plus 1 over 2 up to k of the binomial coefficient km. And when k is actually large, this is also 2 to the k plus things which are negligible compared to k. So you see in both cases, this c of k is exponential in k. Right? So that means that the sum here is involving something which is exponential both in k and in n. It's okay? So now, why is it interesting to look at this v of tau? Because if we, let's focus on one representation tau, for instance. So what are we doing here when we fix tau before we sum over tau? Well, we are back to a perceptron problem. If we fix tau, we fix the value of hidden units. We are just trying to measure the volumes of the JLs which actually map your input onto some tau. Okay, and then maybe some taus are good, some are bad, and so on. But I mean, for a fixed tau, it's a perceptron problem, and we know how to solve it, right? We had done that yesterday. So that gives, I think, a picture which I find nice. I don't know. Then you tell me whether you find the same thing or not. Which is some kind of intuitive picture of what is going on in terms of solution space. So here is my space of all the possible JLs. Okay, it's just a very pictorial way. So for a given tau, you will have a volume which is exactly the one I drew yesterday for the perceptron, right? It's limited by the different hyperplane corresponding to the different x mu's. So I will have maybe some volume here that correspond to one particular tau, right? And maybe if I change tau 1 of input mu equals 16 from +1 into -1, this is still a nice realization, right? It still maps onto the right output for pattern 16. So this is another volume here with a different shape and different volume where I have changed a single bit of my big tau matrix here. I've just changed one sign. Okay? So now you can imagine that you have many different domains. Some of them will be very big. Some of them will be very tiny. But all of them are convex because they all actually solve one perceptron problem. You know, I'm bad at drawing, but I think you see the point here. And so on. And now the problem is not convex anymore. For a given tau, it's convex. But if you look at all the possible tau, it's not convex. Okay? And what I want to do when I compute the volume is actually to sum all these volumes. And you see now that, assuming that if you pick up two solutions randomly, then you need a single Q in order to describe this thing here. That looks a bit strange, right? So there is no reason why it should be true. In fact, we will see that it's true for particular reasons sometimes, but then it fails. Okay, so what I would like to know is actually, I would like to ask some questions about these volumes. I would like to know, first of all, how many domains there are. How many domains of solution? So this number is certainly bounded from above by this to the power p. But many of them will be 0. They will be empty. So I would like to know how many are not empty. Right? I think that's an interesting question. Then you can say, what is the distribution of sizes? There might be big domains. There might be small domains, very small, tiny ones. Okay, so I know that there is a lot of interest in the big ones, right? So we would like to know how big are the biggest ones. of distances between the domains. How further apart are they? And then I have another question, which is, I should increase the what happens if I increase the number of data? This is a snapshot for a given set of data. Now suppose I add one more x, y, which I would like to classify. Then what is going to happen is that the set of solution will be a subset of that, right? So what is the evolution? What is the dynamics of evolution of these domains as I add more and more data? So how do these domains evolve? Evolve with alpha. I mean, increasing alpha. Is it okay for the questions? Okay, so let's try to introduce some tools in order to answer these questions. And the tools are very similar to things we've already introduced. So if you remember in the second lecture, I told you about how we can use a non-zero number of replicas to capture things which were abnormal. Okay? And so I will actually extend this idea to answer the first two questions here. Okay, so what is the idea? So let me look at one domain here, for instance. This is for tau. So here there is, so for the given tau, there will be some volume V of tau. So what I'm expecting is as n is large, how V of tau should scale with n. Well, I mean, you can expect that everything is scaling exponentially with n, right? We are always dealing with these kind of things, right? We are on the hypersphere, so everything. So I'm expecting that I can write V of tau as exponential of n times C of tau, where this quantity should be, mu of tau, where this quantity should be intensive. It does not depend on n when, I mean, it has some limit when n goes to infinity. So that defines the volume of a domain. And now if I want to answer the second question, I would like to count how many domains have a given size, right? So it's an entropy question. So I will define the number of tau such that V of tau is equal to exponential n nu, and that is going to be for me exponential of n sigma of nu. And that's an entropy. Okay? So this is the, is it okay for the definition? I mean, all the definitions are very sloppy here. You should say, okay, how many are between exponential n nu and exponential n nu plus epsilon and so on. Okay, we want it to be clean, but we don't want to do that. Okay, so what can we expect for sigma of nu? It's an entropy curve. So I'm just plotting some possible value of sigma of nu, I mean some possible shape. So you would expect that maybe some kind of bell-like curve. So this is nu, which is the log of a volume, and this is sigma of nu. It's just a guess, actually, and we'll see later on what it is in reality, right? So if you have a curve like that, so sigma is positive here, and then so we're interested in situation where sigma is positive, obviously, because if sigma is negative, that means you don't have anything in large n limit. That's not interesting, right? Okay, so what are the interesting points here? So this is the largest possible value of nu, so that would correspond to the largest domain. That would tell you if you know this nu max, then you know that there is no domain which are larger than that. So it could correspond to the size of this guy, right? So on the other side, you have a nu mean, which corresponds to the smallest one. And there are two other interesting points on this curve. Obviously, the top here, which I will call nu 0. That's the size of the most numerous domains. So maybe these guys here, you know, there are plenty of them. Maybe these ones. And there is another point which is very important here, where the slope is -1. Which I will call nu1. So why is it important? Because you can ask the following question. what is the dominant size of a domain? So one way to say it is, suppose I draw randomly a point, a solution here. I will end up in some domain, right? What is the typical size of this domain? It's some nu. And it will be the nu which dominates the total volume. So nu1 is such that actually this is the R max of sigma nu plus nu, right? So you count how many domains you have of size nu, you multiply by their size, right? And yes?
May I ask you to slightly more? Because I'm thinking of the number of domains of something like 2 to the k. But k is order 1. So
Yeah.
I don't really have exponentially many of them.
No, you have 2 to the k for each mu, so you have 2 to the k to the power p. Remember, this is a matrix. You have 2 to the k here, but then you have p lines. You have one representation for each mu. So it's really exponential in n. Okay? You have to specify the representation for each pattern mu. It's okay? Because for each, okay, I just erased everything there, but that was there, right? You want that for each mu, your representation, your vector tau, is actually mapped onto the corresponding y. And that should be true for each mu. So there are really, I mean, an exponential number of them. But k is finite, I agree.
Yeah, I guess it's then about this figure. So the space of j's, that's like, because I thought what you're plotting there is actually the intersection of the things for all views.
Yes,
That's what it is.
yes. But each small domain here is actually indexed or labeled by one matrix like that. The-
But it's a k times p matrix.
Yes. So they can be disconnected. They can be actually close to each other. You know, it's yes. Yes, a question.
Why don't we assume that there are many domains of size 0 here?
Sorry.
It seems that this distribution has no domains of size 0.
Yes, you are right. So it could be that mu min is at minus infinity, and in fact, it will happen. You will see. It depends on alpha. You're right. I mean, it was just a generic thing, but I mean, you'll see the yes.
Can you explain again how you're defining entropy?
What I could.
Can you explain again how you're defining entropy, sorry?
Okay, so here, so suppose you fix nu, right? So you count how many, you count, imagine you can count the volume of all of your domains, and you do the histogram, and you count how many domains have a size which is like this. So the log of a volume divided by capital N would be nu, and that I define as exponential n sigma nu.
So is there, the symbol on the left and the right are not the same? This is like some,
Oh, sorry. I apologize. That's bad. So this is the number of tau such that the volume is equal to exponential n nu. That I define as exponential n sigma of nu. Okay? Yes?
So is that number of tau supposed to be the number of taus that satisfy the constraint, or not?
Yes, so I mean, that's the total number of taus, the maximum number, but most of these taus, they will correspond to empty domains. So what I would like to compute here is, for instance, how many of these domains are not empty, and you see the answer is given by that.
No, what I mean is, the question is the number of tau that satisfies the product of theta mu,
Yes.
product of mu over theta being positive.
Yes.
So how come it increases with p? So I don't know, I'd expect more constraints, less ways of satisfying them.
On the J's. But if you have more pair of input-outputs, you have more representations. Number of representation is increasing. The volume is decreasing.
Yeah, because when you increase p, you also increase
Yes.
n, right?
Well, I mean, fix n and increase p. You have more data to accommodate, you know, to classify with your network. Each data point will be classified in some way. And each possible way is a tau vector. There might be multiple possible ways, right? And of course, if you have 10 data, or if you have 100 data, so maybe doing the right classification for 100 is much harder. You will have less solutions. But you may have actually many more ways of doing that with 10.
Okay.
Simply because you have more possibilities, I mean, more patterns to do, right? Is it okay?
Yeah, it's okay.
Okay. So it's interesting. I mean, the number is increasing, but the total size would decrease. So it's a funny thing. Okay, so
Another question?
yes.
If you're looking for the new that gives the greatest volume contribution, why is it the argmax? Why is new one the argmax of this instead of say like new times e to the n entropy?
Okay, so I'm just looking at, so what is the total volume? So I have to sum, my total volume is the sum of all possible representation of V of tau, right? Many of these ones may be actually empty. And that I will replace by an integral of a nu of the number of domains having size nu, or log size nu, times the size of one of these guys. And this integral is dominated by nu1, which is the Rmax of sigma nu plus nu. Is okay? That was my argument.
Wait, sorry. Why is the second factor e to the n new instead of just new?
No, because I'm defining, sorry, this is V here,
Oh, it's easy. Okay.
and that's a nu.
Okay.
You don't like my Greek letters.
Thank you.
I'm doing my best in writing, okay.
So sorry, just to be sure that I'm with you still. Did you tell us already how you computed this curve, sigma of u as a function of u?
No, now I'm doing that.
Okay. Because I kind of see where you're going, and
I'm
not sure whether I missed it.
okay. I'm not always doing calculation first. I mean, sometimes I try to get the picture. So, okay, that's a picture.
Just
Yes, and then,
what do we
okay.
expect? How do we get it now?
Yes, okay, so that's the question. Do you agree that there should be some picture like that? And it would be nice to have this, right? Now, the question is how we do that. So we do that with replicas, obviously. What does it change with respect to the standard replica approach? So it's a bit more involved, but not very much. So, okay, so we want to compute this thing here. And so if I want to get sigma of nu, so you see what is interesting is that when we do the replica approach on V, we are actually not treating sigma of nu and nu in an independent way. The only thing we have access to is this thing. If we want to decouple sigma of nu and nu, if we want to get the full information, we need another parameter. So the idea is to introduce some beta here. So it's a new parameter which I introduced. Okay, I would look at this sum here, and you see that obviously that does not affect the entropy, but it does affect this thing here. The volume is put to the power beta, right? So now, if I'm able to do that, so this is not V anymore, this is V only for beta equal 1, but yet it's a well-defined quantity. I mean, I have the right to introduce it. Then in principle, if I change my values of beta, I could get sigma of nu because through the inverse Legendre transform. That's exactly the same trick I explained in lecture number 2. So this, I would expect, is going to be, okay, so I will explain that on this side. So essentially what I will get is, okay, let me explain this maybe more details here. So if I do this thing here, sum of a tau V tau beta, then that should be equal to the exponential n, the max over nu, sigma of nu, plus nu beta. So if I change the values of beta, going to minus infinity on this side to plus infinity on this side, I will get, if I know this quantity for any beta, I can get this quantity by doing the inverse Legendre transform. In particular, beta equal 1 is interesting. Beta equal minus 1 is very interesting. Beta equal 1 is very interesting. But also beta equals 0 because it will give me access to the most numerous domains. Okay, so that is nice. Now the question is how we compute this. So that depends on the quench disorder and so on. So what we do is always the same stuff. We took replicas here and we do the average. And that will give this with here the typical sigma, right? Okay, so now what is the structure of this guy? So now you are accustomed to having n integer and sending it to 0, right? So we can do the same thing with beta. So let's do with beta. Suppose beta is 3. Actually, 3 is interesting. It could be an integer, right? So in that case, I can write this thing here. So first of all, the sum of the power n, I write with the replicas, as usual. That's the same thing as before. And then I have v tau 1 to the beta up to v tau n to the beta. So I need n replicas for my n representations here. But then, if beta is an integer, that I can write as v tau 1 times v tau 1 times v tau 1 beta times.
Really sorry, can you say again what's beta?
Beta is a number. It's a number that I'm introducing because I would like to be able to compute sigma of nu. Okay? And as usual, if I don't put a beta, so which is by standard thing is beta equal 1, which is hidden, I don't have access to sigma of nu. I have access to this guy, sigma of nu plus nu. So if I want to access this, I need actually to tweak the distribution, so I put a beta in front of that. And by varying beta, then I can get the full information. So it's some kind of effective temperature associated to the domain size, if you prefer, which normally is 1. But I mean, when we do a calculation, it could be anything. Is it okay? So now what is going to happen? I have beta copies of that, but beta is a number I choose, and small n of this thing. So how many replicas do I have? Beta times n. Okay? Then we are in safe ground because we know how to deal with that. It's just a standard problem, except that we have beta times n replicas instead of n. With one subtlety, is that now there is no invariance under the permutation of these beta times n replicas. We have permutation within a group of beta, and we have permutation at this level. But we don't have permutation between one of these guys and one of the guys here, because they are not associated to the same representation. So it's a way, if you prefer, it's a way to break the symmetry, but by hand. It's an explicit symmetry breaking, right? A little bit as you do statistical mechanics. You have a spontaneous symmetry breaking when you have a phase transition, but you can also put a force which is actually pushing towards one thing, one ground state, right, in order to break the symmetry. And that helps a lot because you understand what you are doing in a much better way. Okay, so I think I can erase here. Okay, so what is going to be the QAB matrix? So now we had QAB before. So we still have a QAB, but it's a bit more complicated. I need two replica indices because I need A, which goes from 1 to n, and B, which goes from 1 to n. But I need also a replica index for this, which guy I'm picking up here among the beta. And that I will call A tilde, which runs from 1 to beta. So actually, my order parameters now is a big matrix, which is a beta m by beta m matrix. And I will write it as a matrix of blocks here. So these blocks are of size beta. And I have n blocks. So the total size here is n times beta. Okay, and what is the meaning? So if I am within, of course, on the diagonal, we have normalization, so all the overlaps are 1. It's a symmetric matrix. But now the interesting question is what is going to happen if you are within a block or outside of a block. So if we are within a block, what does that mean? It means that you are looking at the overlap between two vector j's here associated to the same representation. So you are asking an interesting question. You are asking, what is the distance or similarity between two guys inside one volume? Okay? So this I will call Q star. So I will put a lot of Q stars in the blocks. obviously I'm making an assumption here. I'm making the assumption that actually I need a single overlap Q star to describe all these domains. That is not true because there are some small ones, big ones, but that doesn't matter because when we do the large n limit, we are going to single out all the domains with the same size, right, for given beta. So it's not as bad as this looks, right? Yet maybe this is not a sufficient assumption, but that's the simplest one I can do. And now you can ask, okay, now let me do two domains which are different or two solutions which are different. And then what is the overlap here? That's Q. Sorry, I need another color. It's Q. And you would expect that Q is actually smaller than Q star, right? And this corresponds to the off diagonal, the off block, sorry, elements. Okay, so you see that now just by this construction, we are forced to do that. We cannot have a replica symmetric assumption anymore. That wouldn't mean anything. So we are forced to do a one-step symmetry breaking. That's exactly the same structure as Parisi symmetry, Parisi RSB ansatz, with the big difference that beta is the parameter that you choose. You don't optimize over beta. That's the main difference, right? In Parisi ansatz, you have the M breaking point, right? And you should optimize over it. But here, no, it's your choice. But we have to optimize over Q and Q star, right? Okay, so you can do the calculation of these guys here, and you find that the whole thing here, it's again the standard calculation, right? So there is no, I mean, you can do it with all the techniques we have seen. You find that this is something which is a function of, okay. So it's a function of Q star, Q, and then it depends on the parameter alpha and beta. So you see that once we have this thing here, then we can match with this here, and by doing the inverse Legendre transform, or sorry, I should optimize over Q and Q star, right? So I need to extremize over Q and Q star. And then once I have that, I have a function of alpha and beta. I do the inverse Legendre transform, and I get the entropy sigma of nu, which itself is a function of alpha. I forgot to mention that. So there is an interesting point I want to mention, because I think it's important, is that what happens if you take this expression, that you can compute explicitly, and you set beta equal 1? What do you get? Sorry? You get the original volume, but is this function, how will it depend on Q and Q star? Will it depend on the two overlaps? No. It cannot depend on Q star. For beta equal 1, you don't have overlaps within these guys because there is a single one. So in fact, if you do beta equal 1, that gives you exactly the GRS of Q and alpha I wrote at the beginning. Okay? But now, by looking at the vicinity of beta equal 1, you get an extra information, which is the size of the domains which contribute most to the total volume. Okay? Which is completely hidden in the usual calculation.
Can we get a distribution on the sizes?
Yes, so actually, as you vary beta, you will see that the Q and Q star will vary. And the nu also, right? I mean, we want to get the full entropy curve. So as we vary beta, we vary the slope actually where we are. Beta is the slope, so we vary where we are. And we have a given Q and Q star that correspond at this given nu, right? Okay, so what do we get if we do that? So I'm giving you results. So I will first, the most interesting case are beta equal 1 and beta equal to 0. The dominant volumes and the most numerous volumes. So I will give you a result for the parity and committee machines. But actually, okay. Okay, so let me do beta equal 1. That corresponds to the dominant volumes. Okay, so if you compute, okay, so if you compute the Q star, so let's do the parity machine first. So Q star you can compute, and it's going to be 1 minus C over alpha K squared, where I'm not writing the constant here, but they are known, right? We get Q equals 0. We get sigma 1 equal to log K minus alpha log 2. This is true when K is large and alpha is, well, in this regime. Otherwise, it's actually a little bit difficult to compute. So imagine that K is large, alpha is large, but small compared to K. So what does that mean? Q equals 0 means simply that actually your domains, your important domains, they are essentially orthogonal to each other. They are totally uncorrelated, right? Q star is here very small. I mean, very small, sorry. Q star is very close to 1. So why does it depend in this way? Actually, that it's clear that this is the important ratio, right? But because, I mean, the alpha which matters, the important alpha, relevant alpha, is obviously the comparison, the ratio between P and N over K, which is the size of the number of components in one vector. So this is P over N times K, and that I call alpha, right? So clearly, that corresponds to a single perceptron domain, and you would expect that it will scale like that when P over N becomes large. That's actually exactly the kind of learning curve, I mean, the kind of curve that you see when you approach the capacity, you know, and you see that the Q is shrinking for a single perceptron. So what we have is a picture where there are many, even the dominant volumes, they are pretty small. They have a Q which is actually close to 1, and they are very far away from each other. So it's not at all the perceptron case where you have a single domain, which is what it is. Here they are scattered all over the place. And this is the number, or the log of the number, the entropy. Okay, so for the committee has a different. Yes?
What should I think of getting from this sigma 1 as an absolute number, like?
So.
There? What does it mean? I mean, given like that as an absolute number, what does it mean?
As an absolute number, well, okay. So what does it mean? It means that if I look at the number of, remember what it means. This is the number of volumes, of dominant volumes. Okay? So you can compute the exponent of that. So it's exponential n log k minus alpha log 2. Okay? So it gives you how you have, and you can compare to what you could have at the maximum, which is this 2 to the k times alpha n.
So that's what I should compare it to?
Yes. So that's the maximal possible number of representation you can think of. And you see that there are only a few of them which actually correspond to that give you the large volumes. You know, log k and here k. It's nothing when k is large, right? Okay, and you see the way it depends on alpha, okay? So that means that most of this, but I will come back to that. Most of this representation, they are totally useless. They do not contribute to the total volume of solution. Okay, so what that means, okay, so that was for the parity machine. If you do the committee, so the committee, you have Q star, which is of the same order. And you have Q, which now also is shrinking. It's minus the constant over alpha squared. So that means for the committee machine, you have very small domains, but they are closer and closer to each other when you increase alpha. Okay? They look like the same in terms of solutions. Okay, and you get the same sigma 1 to dominant order. So what does that mean? That means that if I look now at sigma 1 as a function of alpha, I plot it. You see, I'm starting here from log k. Then I'm essentially, okay, sorry, the sigma 1 is not the same for the committee machine. I said something completely wrong. That was the parity. The committee is log k minus 16 over pi. So it's a 16 over pi. Never remember. No, pi over 16, sorry, alpha squared, plus terms of the order of log alpha. No, it's not the same. Okay, so for the parity machine, you see a linear decay, and then it will hit 0 in alpha 1, which is log k over log 2. Okay, and for the community machine, it's a number which is of the order square root of log k. So what does that mean? That means the following thing. If I am below this number, alpha 1, sigma 1 is finite, which means that I have an exponential number of dominant volumes. So it means that if I pick up two solutions at random, my first solution at random, it will be with high probability in one of these dominant volumes, by definition of the dominant volumes. I pick up another one, it will be on one of these dominant volumes, but since I have an exponential number of them, they will never be in the same volume. So if I measure their overlaps, I will find Q. So even if I have all these scattered domains which are all over the place, the replica symmetry on that is exact. But not because there is a single domain, but because there are many of them, right? Because there is an exponential number of them. So you have two ways to have replica symmetry, either a single one, single guy, or an exponential number of them. So it's true that up to this range here, up to this alpha 1, the replica symmetric solution should be correct. But as soon as we go above alpha 1, then it's not. Because now we have a non-exponential number of domains. So controlling exactly the number of domains is very hard. But imagine you have a finite number of domains. Then, of course, you have a finite probability of picking up the two guys in the same domains. So you could end up with Q star, right? So it won't be Q anymore. So obviously, this bound here tells you that replica symmetry is wrong above this alpha 1. Okay, so what that means, if you look at how these things decreases here, is that in the perceptron learning problem, we had one domain which was shrinking. And now we have so it was a shrinkage scenario. Here we have a more complex scenario where on top of a shrinkage, we have it, because this is going closer and closer to 1 as alpha is increasing. We have also a pruning process where most of the domain, they just get rejected as we impose, we have more and more data. So that means each time you add some data, then you are simply getting rid of this domain, right? You add one more data, and then you get, and the remaining domain, they shrink. So you have a double process where you have both shrinkage and pruning, which is something which is seen also, in random combinatorial optimization problems. Okay, so what about the most numerous domains? So to get the most numerous domain, do you all agree that I should do beta equal to 0? Yes? That's the one that would select the top of sigma, right? So you have to do the inverse Legendre transform. So I'm not doing the calculation here because it would be heavy, but it's not difficult. Okay, so when you do the calculation, what you find, okay, so let's look at very small alpha. Suppose I have very few data. Then obviously, if my alpha is smaller than 2 over k, which is the critical capacity of a perceptron, then virtually all representations are implementable because I'm below the critical capacity of each perceptron, right? So that would expect that here in this regime, all my domains, all my representations are possible. So that means that the sigma 0 should be 1 over n log of 2 to the k times alpha n. So it should be alpha k log 2. So if I plot sigma 0 as a function of alpha, so you see that to answer your question, I mean, you get more representation even if the full domain is, the full volume is shrinking, right? Simply because you have more things to classify. So it should increase linearly at the beginning. and we just saturate the possible number of implementable representation. That is true up to alpha equal to 2 over k. But then it's not going to be true anymore, right? Because then we are above critical capacity for a perceptron. So that means also the Q star of these things will shrink. So you see, if I look at the Q star, which is the size of these domains here, the intra-domain size, then it will go to 1 at the capacity, right? So that means Q star is 0 here, then it's 1 here, actually, and it keeps being 1 at larger alpha. So that answers your question. That means that the true, if I am above this critical thing here, the curve for sigma of nu is not the one I draw. That's not true. It's something like that. With asymptotically beta equals 0 at minus infinity. So that in the most numerous domain, they have a size which is essentially vanishing. So that means they are smaller than exponential minus n. Don't know exactly what they are, but they are very, very small and very numerous. Okay, so now you can compute the curve. So we have an explicit expression for the parity machine, but we don't have an explicit expression for the committee machine. I mean, just asymptotic one. So this one is correct. So that's alpha k log alpha k minus alpha k minus 1 log alpha k minus 1 minus alpha log 2. So if you plot this guy, then it's below this maximal number for possible representation, but it's still increasing. It will have some maximum, and then it will become 0 here. So the maximum is for alpha when k is large of the order of log 2, and the maximum is order log k. So you see that the most numerous domains, they are more or less of the same order of magnitude in terms of entropy as the dominant domains on the log k scale. That means I should rescale all my sigma of nu by log k, and then it would go to the same thing. You know, the top domains, I mean the most numerous one and the dominant one, they would be very close on this scale, right?
But didn't you require alpha much bigger than 1 for sigma 1 to be log k?
Yes, we have to be in this regime, right? So,
But then it's log 2, right? So it's not.
sorry?
Sorry, I thought now you're talking about alpha equal log 2.
No, yes. So for alpha equal log 2, we are here, right?
But
It's
alpha
more-
equal log 2, is that 2 or not so much? That sigma 1 equal log k?
Oh, no, this result is in this regime, right?
Okay.
Yes. So yes, okay. It's a little bit shaky here. But I mean, yes. So we have to be in this regime, right? So you need k large and we have to be away from there, right? So I'm not saying the two curves are equal. They're not. I'm saying they are the same order of magnitude in terms of log k, right? And the point it crosses here is to the largest order, dominant order, log k over log 2, which is alpha 0, which is the same as alpha 1. So that's a good sign that it is actually the critical capacity. That's alpha c, which has nothing to do with the k square given by replica symmetry, right? So with the committee machine, you find a similar behavior with a capacity. I'm just finishing that.
Was alpha 1? Log k over log 2.
But we find the same with alpha 0.
Oh,
Yes, they coincide. The whole thing is shrinking and disappearing. And then that means you don't have any solution anymore. So that's the capacity. And then here you find also, so the capacity, so the sigma 0, the alpha 0 is also equal to alpha 1, I mean to dominant order in log k, right? And this is square root, this is 16 over pi times the square root of log k. Okay, so one more thing about this picture. Now you can ask, okay, that was for random data. What happens if I do generalization? Suppose I have a parity machine. This is my teacher with some weights, and it's producing some outputs. And then I have a student parity machine, which is trying to learn the association, right? It's always the same framework. What is going to happen? So we are, let's take the parity case because it's simpler. So I am in this scenario. Remember, Q is equal to 0 and Q star is actually pretty big. So Q is equal to 0. So now you ask, so what is, where is my teacher? in this landscape. The teacher is a point there. It's a solution because it's actually the teacher by definition is always right. So it's always produce the right output. So it's somewhere. It's a solution of this problem. So if you pick out randomly your teacher, for a random teacher, it will be in one of the dominant domains, by definition of the dominant domains. So the teacher is in one of the domains which correspond to beta equal 1. Okay? Otherwise, you have a biased teacher. So the teacher is somewhere. This is your teacher. And now you see what is going to happen. If you impose, for instance, that the training error is 0, if the number of dominant domains is exponential in n, and this is below alpha 1, there is no way that your student will be in the same domain.
That's true for the parity.
Yes, for the
community.
You are right. I'm talking about parity here. So with the parity, you will have 1/2 generalization error, so that is you cannot generalize at all, as long as you are below alpha 1. So the generalization error will be 1/2, as long as you have an exponential number of dominant domains. Once you are, when they are not exponential anymore, then these guys can be, and the student and the teacher can be in similar domains, in the same domain, so then the error will decrease, and asymptotically it will be as a single perceptron problem, so it will be 1/alpha. Okay? So for the committee, Lenka, you're right, that's different because Q is not equal to 0. Q is actually close to 1. That means the domains, you have an exponential number of them, so the teacher and the students, they are not in the same, as long as you have an exponential number of them, but they are not too far away, these domains. So it's not so bad. So the generalization error is actually decreasing because this Q is close to 1. And then at some point when you don't have an exponential number anymore, then they will fall in the same domain and then it will decay even faster. Yes?
Imagine that at the beginning I enforce the constraint on the J's. Even either both on the teacher and student or only on the teacher or only on the student. But if I, for instance, if I enforce the constraint that the student weights are orthogonal, this would be the Q equal to 0, right? Even in the column.
So you impose that.
At the beginning, I include an additional constraint. This is because Darfin proposed a problem.
You want a student very different from the teacher.
I want I want the units. The weights of the student, the JL, if you want, to be orthogonal between themselves.
Oh, orthogonal between themselves.
Yes. This is not probably what people probably Darfin.
But here for me, there are. I mean, in this tree-like architecture, they are orthogonal.
Okay.
So I'm not referring to that. I'm referring really to the similarity between the student. So the same JL and the same TL for the same L,
Okay.
right? Okay, so what you are saying is interesting in the case when you don't have a tree-like architecture anymore. Then that's interesting. So what happens if you don't have a tree-like architecture? So essentially the main effect is that instead of having n over k weights to each hidden unit, you have n. So essentially you multiply the capacities by k. It's not exactly true. It's true for the parity machine. So instead of having log k over log 2, you get k. And for the committee machine, it's not true because the hidden units, they are not independent anymore. That means the Q you were mentioning, the QLL prime, is not equal to 0. Okay, it's tiny, but not equal to 0. It does contribute. And that instead of giving 16 over pi times k square root of log k, it gives 16 over pi minus 2, if I remember correctly. Which is not a big change, right? But I mean, that's a trace of the correlation between the hidden units. Yes?
About the teacher-student setup. So I agree that alpha 1 matters for when in principle it is possible to find a teacher. But that does not imply that we actually have algorithms that will be able to do it efficiently.
Yes, I agree.
And we actually don't, right?
I agree.
Too much farther.
I agree. Yes, I was here in the ideal situation where you are able to. Yeah. Yes, I agree. Yeah.
And you have a...
But if you are able to satisfy that all the constraints are equal to 0, you should be, well, okay. Yeah, okay, so your algorithm is going to bias the distribution, right, over J's. So it will not be exactly this measure. Here, that was a flat measure of all possible solutions, but the algorithm is going to bias that, so it's going to be something else. I imagine a perfect algorithm here, so obviously it will change the picture. Anyway.
because, I mean, from what I remember, for the algorithm to work, you need actually alpha that is not like k log k. There is an additional k, like it's really a lot.
For the committee, you mean?
For the committee.
Okay. Okay, so maybe we can talk about that. Yeah, yeah. Okay, yes?
From this analysis, it would seem like one would prefer a committee machine like architecture rather than a parity machine because you can have better generalization. Like, even
Yes.
in the case. So, is there a particular scenario when you would prefer parity machine over?
Yeah, I mean, so in reality, actually, you should learn the decoder, right?
Yeah.
So that I'm not doing here, right? But if you impose the decoder, I agree with you that having a parity machine is not a very nice thing because it doesn't learn very well. I fully agree, right?
Is there any scenario in which it would be better, or there is no setting in which it would be better?
Well, I mean, if your rule is given by a parity machine, right? I mean, I don't know what to answer to that. It depends on the data, right? Okay, so I just want to say one more thing, but then I'm not sure. Okay. So there is a nice application of these ideas, which was on a model of a realistic neuron, which is called the temportron model. I don't know if some of you already heard about it. Yes? Very good. So it's a model which was introduced by Robert Gutisch and Chaim Sopolinsky 2006, if I don't make a mistake. So it's a model which is supposed to be a better, I mean, it's not supposed, I mean, it's certainly more realistic than a standard neuron we have considered so far. But I'm not sure I have time to explain it. Maybe Chaim is going to tell you something about tempotrons. If you're interested, I can tell you. So I'm just writing this. Tempotron is a perceptron, so it's classifying as a linear classifier, but then time matters. That means your inputs, they vary with time. So you are doing a time-dependent classification task, which is quite interesting. And the domain of solution is now, even if it's a perceptron, due to this constraint over time, is actually of this shape here. It's highly non-convex and it's quite complicated. Do I have 10 minutes now still, I think?
Yes.
Okay, so I would like to show you the second part. I don't know if I have enough time. I don't know how to put the... yes, thank you. So in the second part, I would like to talk about embedding low-dimensional manifolds in a recurrent neural network. And a little bit about the motivation. So I don't know how much time I'll try. Thank you. Okay. Okay. So that's something I already told you a little bit about yesterday. And it's deeply connected to the perceptron. So we are moving back to the perceptron architecture, but in a slightly more involved context of recurrent neural networks. So essentially the problem is, imagine you have a recurrent neural network with some kind of dynamics here, which is a very simple dynamics. So the neurons are +1, -1, or 0, 1. And let's say +1, -1 here in this formulation. You have your configuration at time t, you multiply by the j, so you take the sign, and then you just iterate this dynamics, right? And you have a jij matrix here. So the question that was asked a long time ago is how you can embed some fixed point of the dynamics here. I mean, and that was essentially the idea that John Hoffield had when he discussed the idea of auto-successive memories, right? So you like to build the jij in order that such fixed point that you like, I mean, some configuration that you like will be fixed points of this dynamics. Then, of course, there are a lot of questions about the size of the basin of attraction and how many fixed points you can implement. And this is the same problem as the perceptron. I already mentioned that very briefly yesterday. And why is it the same problem? Because imagine you have a set of neural configurations. So I is the index of a neuron, and mu is the index of a configuration. So this set of fixed point conditions are just that xi mu is a sign of this, right? And now you see, that's exactly the same thing as the perceptron, where the output y mu is actually one component of this vector, right? So you can solve this problem row by row of the jij matrix. They are just independent, so you have n rows, and they are just n independent perceptrons that you had to solve with the same data. So the answer is that as long as P over n is smaller than 2, then you can do that with random, from random data, right? So you will always be able to embed P random configuration into an n-dimensional recurrent neural network. Okay, it's nothing else than the perceptron problem. You agree on that? Okay. So now the question is, what happens if you have correlated data? So if you are in the perceptron, the standard perceptron model, where the output is not the same thing as one component of a vector, actually the correlation do not matter much. But if you are in the case where the y mu is 1 over xi mu, it can affect a lot the properties. And I would like to give you a motivation to try to build actually a more complicated set of fixed points, where actually we'll have a lot of fixed points which are close to each other here, and another set of very close fixed points there, and all these set of fixed points are far away from each other. So why do we want to do that? So one motivation was already given, as I told you, with this, for instance, MNIST, this idea that a lot of data points can actually be embedded on low-dimensional manifolds. But there is a very strong motivation coming from neuroscience, and I know that some of you are already experts in that. And I just want to brief that, to flash that very quickly. There are beautiful discoveries in the 70s by O'Keefe and collaborators of the place cells in the hippocampus. So who has never heard about place cells? Okay, some of you have never heard. So place cells, they are cells which are found in the hippocampus. It's a region which is found in all mammals, and to some extent in all vertebrates. And place cells are cells which fire, they become active when you are at some position in some environment that you already have experienced. So when you enter a new environment, you will learn a map of this environment, which is called a cognitive map, and these cells will associate a position to their activity, right? So there will be a mapping between the identity of a cell and your position in this environment. It's a beautiful discovery, right? It's very useful for many, many different things. They are not the only cells which depends on position, but they were the first ones which were found. So place cells, you need visual stimuli. I mean, essentially to build these place cells, this place cell representation when you enter a new environment. But if you switch off the light, the place cells are still there, and essentially you update your position in this map by integrating your motion and so on, right? So there are very nice things, and so there have been hundreds of thousands of papers on these place cells. Okay, so now the question is interesting is, how can we actually store multiple environments in the same network? We have a single hippocampus on each hemisphere, but we know many, many environments, right? Or we know also several representations of the same environment which depends on the context. And so there have been experiments where you can show that an animal, depending on the situation, you know, a nice situation with food, a bad situation with predators, for instance, but it's the same environment, will actually have completely different representation because the spots which are important in the two situations are completely different. So the map should help guide the animal towards the important or the relevant position, right? So the question I'm asking here is, how can we embed? You know, a map here is, for instance, for an animal living in a plane, is a two-dimensional attractor, where you can represent with n neurons, a large number of neurons. So in rats, there are about 300,000 neurons in the hippocampus. You represent a two-dimensional coordinate. So you want not fixed points, but you want a fixed plane. For instance, your representation, they should code for one collective coordinate, which is the position of the animal. Okay? And in fact, we would like to do that. So here it's a one-dimensional attractor, which is a ring. But we would like to be able to have multiple continuous attractors embedded in the same recurrent network, which is our model for the hippocampus. And each attractor would be one map for one environment. So I'm going very fast here, but I hope you get more or less the idea. Okay, so how do we connect that to the perceptron problem? So the idea we had recently was very simple. So let's try to simplify the problem. So instead of having purely continuous attractors, let's try to have this kind of thing. So what I will do is that I will have my fixed point now. There are discrete attractors. But if I want to represent a continuous attractor, then we have a lot of fixed points which are very close to each other here, right? So formally it's not continuous, but if you put a lot of fixed points which are very close to each other, you can imagine actually it will be easy with a little bit of noise in the dynamics to jump from one attractor, and essentially it will correspond to a continuous version, a little bit noisy version of a continuous one. Okay? So now there is an interesting question, which is, what is the trade-off between the accuracy you want to have on one attractor like that, which is, let's say, controlled by epsilon, the distance between neighboring fixed points, or if you prefer, something which is related to the inverse of the number of points along an attractor, and the numbers of attractors you can embed. So we are back to a perceptron problem, because I would like to memorize many fixed points in a recurrent network, and you know, I just remind you, it's a perceptron problem. So it's a simple problem from a computational point of view. What is harm now is that you have a lot of correlation between the representation, this pattern of activity here, because they are all built from a very low dimensional coordinate, right? So just to be more precise, so how this can be done. So you can imagine if you want to mimic the place field, so what you can say, okay, for instance, this is my first environment. So here I do it only with 5 neurons, which have different colors. I will assume that each neuron has a place field. So it's a region in the environment, which is a square here, where it's active. So here you see 3 positions of the animal. So when the animal is here, the pink or red neuron is going to be active. You have periodic boundary condition here. It's going to be active. The yellow is going to be active, and the other ones are silent, right? If the animal is here, nobody is active. Okay, so depending on the position of the animal, you have different activity patterns, and that corresponds to what you would like to have as fixed points of your networks. And you do that for different environments, and a different environment is a completely different association between the activity and the position. So we have the same place cells, but I have one place cell which is firing because I'm here. This is the 4th lesson, so I know this environment. Over the last 30 years, actually, I hope I kept the same representation for 30 years. I'm not sure, but actually, there are interesting experiments about aging rats where you see the representation become fuzzy. Actually, but anyway, so what you see, okay, so I know, but I can use the same place cell when I am in my office at ENS in Paris. And then they will code for a completely unrelated position, right? So you have the same repertoire of cells, which code for different positions. And what makes unique an environment is the pattern of pairwise correlation between the cells, right? Some place cells can actually be activated by the same position, essentially, in one environment, and they will never fire together in another one. So the matrix of pairwise correlation makes this signature of an environment unique. Okay, so you create this data. So you can imagine that you have random position of the place fields in several environments. So you have data which are created this way, and then we want to try to solve the perceptron problem. And that we can do using standard SVM techniques, right, to find the best solution. So what I want to find is the J matrix, which has maximal stability. That's the kappa I introduced yesterday, right? That's always the same stuff. That is, you take all your maps, mu, all your points you would like to position of the animal or points you want in your map number mu, and that defines a vector of activity, and you would like that this thing here has the same sign as this one. I use x equals 0,1 instead of plus minus 1, it's the same thing, right? And the minimum over all position, all maps, and all neurons is the stability. And you want to maximize this minimum thing. So this is done with standard SVM algorithm. So I'm just showing you an outcome, and then I will just sketch the result. So here is for a single environment with 1,000 neurons, and you just draw randomly 300 points, right? And you learn the best matrix. So it's a 1,000 by 1,000 matrix. And then what we do, instead of running this dynamics, we just put a little bit of noise here. So, you put a small temperature so that sometimes when the argument is positive, you have a 0x, or sometimes when it's negative, you have a plus 1x with a small probability. Otherwise, it gets to the fixed point. Okay, so, and you see what happens. So here, the position of the points are the red crosses, and each time a neuron is active, we put a blue dot at the position. And it's just a Monte Carlo simulation, right? So what you see is a kind of coherent set of neurons which activates, of course it's noisy, but the center of mass, really, it's coherent. You have a well-defined center of mass which actually moves over time. And here there is this pure diffusion. It's just due to the noise, right? So essentially, the distance between these fixed points is so small and the attractor is so large that actually with the noise it diffuses in a kind of unbiased way here.
So I got lost. What is getting optimized here?
What is, sorry?
What is getting optimized here? The J's?
Yes, I optimize the kappa, the stability.
And you're changing the J's?
The J's, they are learned with this prescription, and then I'm just running the dynamics over the neurons. Okay?
Okay.
So I just want to show you now briefly an example where you have, two environments. And then maybe I should stop because it's already late. I wanted to give you a capacity, but I won't give it. Okay, so you see, so two environments. So what is going to happen is that, of course, you have a single set of neurons, but sometimes you see a coherent representation in the first environment. That is the neurons which fire, they correspond to nearby position in the first one, and sometimes it jumps to the second one through some purely random process. We have to wait at the end, but you see it at the end. Then it's coherent in the second one. See, you get the bunch, and then it jumps back and so on. So you see that you have the attractor, and you can really move on a cycle on the manifold, and then sometimes move onto the other, and then jumps back and so on. And it's purely random.
Sorry, I'm completely lost. What do the red points correspond in equations?
The red points correspond to the position here, which defines some patterns of activity. And I want them to be close to each other in order to define a manifold. So I have a manifold. I will look at many positions randomly. I define the pattern of activity correspond to these points. And then I learn that in a perceptron.
So they are encoded in the JJs.
Yes, the JIJ is encoding the fact that all these points actually correspond, all these pattern of activity correspond to nearby points in the manifold. Yes. But the statistics here, the low-dimensional statistics of the activity patterns is very important. Okay, so maybe I will stop here because I am really running out of time. And then if you have any guess about this trade-off, I'm happy to, this trade-off I was mentioning, I'm happy to hear about your guess at lunch, for instance. And then I can give you the answer. Okay, I'll stop here.